charged particles from one object to another object. In previous standard, we also studied about electric current. In this chapter, we will study about an electric current flowing through a conducting wire, an electric current flowing through a resistor, electromagnetic induction, electric motor, and generator. Energy transfer in an electric circuit. Try this. Materials: connecting wires, electric cells, electrical resistance, voltmeter, ammeter, plug key. Procedure: connect the circuit as shown in the accompanying figure. After taking the components with proper values, measure the current I. Also measure the potential difference VAB between the two ends A and B of the resistance. The potential at A is higher than the potential at B, as the point A is connected to the positive electrode of the cell and the point B to the negative electrode of the cell. If a charge Q flows from A to B, work ABQ has been done on Q. While going from A to B, from where does the energy come to do this work? The source of energy is the cell. The cell gives this energy through the charge Q to the resistance where work VABQ is performed. If the charge Q flows from A to B in time t, that is, the work is performed in time t, then during that time the energy VABQ is given to the resistor. What happens to this energy? This energy is received by the resistor and is converted into the heat energy. The temperature of the resistor is increased. Use your brain power. If in the circuit the resistor is replaced by a motor, in which form will the energy given by the cell get transformed into? P is equals to electrical power is equals to energy upon time required is equals to VAB Q upon T is equals to VAB I. Therefore, Q upon T is equals to I. The source of energy the cell gives in the time T, the energy P into T to the resistor. If I is the current flowing continuously through the circuit, the heat produced in the resistor in time T will be H is equals to P into T is equals to VAB into I into T. According to Ohm's law, VAB is equals to I into R, H is equals to V square AB into T upon R. Similarly, H is equals to I into R into T is equals to I square into RT. H is equals to I square into R into T is called Joule's law of heating. Unit of electrical power. P is equals to VAB into I is equals to volt into M. 1 volt into 1 M is equals to 1 J upon 1 C into 1 C upon 1 S. 1 J upon S is equals to W watt. Thus the unit of electrical power is 1 watt. Heating effect of electric current. When a resistor is connected in an electrical current, heat is produced in it due to the current. This is known as the heating effect of current. Equipment such as water boiler, electric cooker, electric bulb make use of the heating effect of electric current. Electrical conductors having higher resistivity are used here. For example, a coil made up of an alloy nichrome is used in the electric heater cooker as a resistor, while a tungsten wire is used in an electric bulb. Because of the current, this wire gets heated to nearly 3400 Celsius and emits light. The hot wire also radiates heat to a certain extent. Several times we hear or read about a building catching fire due to short circuit. Sometimes if we switch on an equipment in a house, the electrical fuse wires melts and the electric supply shuts down. Let us discuss about the cause briefly. The home electrical connection consists of live, neutral and earth wires. The live and the neutral wires have potential difference of 220 volt. The earth is connected to ground. Due to a fault in the equipment, or if the plastic coating on the live and the neutral wires gives away, the two wires come in contact with each other and a large current flows through it, producing heat. If any inflammable material such as wood, cloth, plastic, etc. exists around that place, it can catch fire. Therefore, a fuse wire is used as a precautionary measure. We have learned about fuse wire in the previous standard. As soon as high current flows in the circuit, the fuse wire melts and breaks the circuit and a mishap is avoided. Many times, particularly In the summer season, huge electrical power is used in the evenings due to home lighting, fans, air conditioners, use of electricity in shops, etc. As a result, excessive current is drawn from the transformer supplying the electricity, and if the capacity of the transformer is insufficient, its fuse wire melts and the supply gets shut down. Such events occur due to overloading. Always remember, the unit of electric power 1 volt is a very small unit. Hence 1000 volt or 1 kilovolt is used as a unit to measure electric power. In practice, if 1 kilovolt power is used for 1 hour, it will mean 1 kilowatt into 1 hour of electrical energy is used. 1 kilovolt hour is equals to 1 kilowatt hour is equals to 1000 watt into 3600 S is equals to 3.6 into 10 raised to 6 Ws is equals to 3.6 into 10 raised to 6 J. Do you know, these days miniature circuit breakers MCB switches are used in homes. When the current in the circuit suddenly increases, this switch opens and current stops. Different types of MCBs are in use for the entire house. However, the usual fuse wire is used. Magnetic effect of electric current. We have learned about heating effect of electric current. In previous standards, we have studied about magnets and magnetic lines of force. However, it will be interesting to see if an electric current and magnetic field are related to each other. Try this. Connect the circuit as shown in figure. Connect a copper wire thicker and straight as compared to the connecting wires between A and B. Keep a magnetic needle adjacent to the wire. Keep the plug key open in the circuit and observe the direction of the needle. Close the plug key and observe the direction of the needle. What do you notice? Now interchange the connecting wires connected to the cell and observe the direction of the magnetic needle. Do you notice any relation between the direction of current and position of the needle? What do you learn from this experiment? The magnetic effect is observed because of the current in the wire. This means electricity and magnetism are closely related. On the contrary, if a magnet is moved and kept moving, will we observe any electric effect? Is it not exciting? Therefore, we are going to study magnetic fields and such electromagnetic effects. Finally, we will study the principles, construction, and working of electric motor and electric generator. Try this. Connect the circuit as shown in figure. When a large current, approximately 1 A or more, flows through the thick copper wire passing through a cardboard, the magnetic needle kept at different points on the cardboard around the wire stands in different directions. Mark this direction with a pencil. Discuss with your friends and teachers about the requirement of the current, number of cells, cells of what potential difference, thickness of the wire, etc., and then perform the experiment. The direction of the current shown in the circuit is its conventional direction. What changes are caused by increasing or decreasing current? What do you see when the magnetic needle is kept a little away from the wire? Now instead of magnetic needle, spread iron filings on the cardboard and observe. The iron filings arrange themselves in a circular manner around the wire. Why does this happen? You have studied magnetism and magnetic field in previous standard. The iron filings spread along the magnetic lines of force. Always remember, a magnetic field is produced around a straight current carrying conductor. If the current is unchanged, this magnetic field reduces as the distance from the wire increases. Therefore, the concentric circles representing the magnetic lines of force are shown bigger and rarefied as the distance from the wire increases. If the current through the wire is increased, the intensity of the magnetic field increases. Right hand thumb rule. This is the conventional rule for finding out the direction of the magnetic field produced by a current flowing through an electrical conductor. Imagine that you have held the conductor in your right hand in such a way that your thumb points in the direction of the current. Then turn your fingers around the conductor. The direction of the fingers is the direction of the magnetic lines of force. Magnetic field produced by current through a circular loop of a conducting wire. We learned about the magnetic lines of force of a magnetic field produced by a current flowing through a straight conductor. What will happen to the magnetic lines of force of the field produced by a current flowing through a loop made by bending the straight wire? A circuit is completed by connecting various components as shown in the figure. If the current passes through the loop, the magnetic lines of force are produced at each point on the loop. As we go away from the wire, concentric circles representing the magnetic lines of force will become bigger and bigger. As we go towards the center of the loop, the circle becomes so big that its arc can be shown as a straight line. In figure, the magnetic lines of force are shown near the points P and Q only. However, they will be created near each point on the loop. Likewise, each point will produce magnetic field at the center of the loop. By making use of the right hand thumb rule, check that every point on the loop contributes the magnetic lines of force at the center of the loop, and these lines of force at the center of the loop are in the same direction. The intensity of magnetic field at any point produced by a current flowing through a wire is dependent on the current. As we have seen in the experiment, this means that if there are n turns in the loop, the magnetic field n times of that produced by a single loop will be created. On discussing with your teachers, with their guidance, see if you can perform the above experiment by collecting appropriate materials. The direction of the magnetic field can be determined with the help of a magnetic needle. Magnetic field due to a current in a solenoid. When a copper wire with a resistive coating is wound in a chain of loops like a spring, it is called solenoid. Whenever an electric current passes through a solenoid, magnetic lines of force are produced in a pattern as shown in figure. You are aware of the magnetic lines of force of a bar magnet. The properties of the magnetic field of a solenoid are very similar to the magnetic field produced by a bar magnet. One of the open ends of a solenoid acts as a magnetic north pole and the other as the magnetic south pole. The magnetic lines of force inside the solenoid are parallel to each other. What does this mean? This means that the intensity of the magnetic field within the solenoid is uniform everywhere. That is, the magnetic field in a solenoid is uniform. Force acting on current carrying conductor in a magnetic field. Try this. Materials: flexible copper wire, stand, electric cell, a horseshoe, magnet with a strong magnetic field. Procedure: using the stand, fix the copper wire so that it passes through the poles of the horseshoe magnet as shown in the figure. Connect the circuit as well. What do you observe? Whenever a current is not flowing through the wire, it remains straight. Position A. When the current flows from top to bottom, the wire bends and comes into position C. If the current direction is reversed, that is, it flows from the bottom to the top end, the wire bends but comes in the position B. This means the direction of the force on the wire is perpendicular to both the magnetic field and the direction of the current. Here, the direction of magnetic field is from N to S, H. In this experiment, it is noted that whenever current flows through a conductor in the presence of magnetic field, a force is exerted on the conductor. If the direction of the current is reversed, the direction of the force also gets reversed. If the magnet is kept reversed, that is, the south pole is brought at the position of its north pole, and its north pole brought to the position of its south pole, what will happen? The above experiment clearly shows that a force is exerted on the current carrying conductor. The direction of this force depends on both the direction of the current and the direction of the magnetic field. Experimentally, it is possible to show that this force is the maximum when the direction of the current is perpendicular to the direction of the magnetic field. How will you do this? Fleming's left-hand rule. In the above experiment, we considered the direction of the electric current and the direction of the magnetic field and found that the direction of the force exerted is perpendicular to both. There is a simple rule relating these three directions. This rule is called Fleming's left-hand rule. According to this rule, the left-hand thumb, index finger and the middle finger are stretched so as to be perpendicular to each other. If the index finger is in the direction of the magnetic field, and the middle finger points in the direction of the current. Then the direction of the thumb is the direction of the force on the conductor. Electric motor. You know various forms of energy. You also know that energy can change its form. A device changing electrical energy into mechanical energy is known as electric motor. Around us, in our day-to-day life, an electric motor is a boon. It is used in fans, refrigerators, mixers, washing machines, computers, pumps, etc. How does this motor work? The electric motor consists of a rectangular loop of copper wire having resistive coating. As shown in the figure, it is placed between the north pole and south pole of a magnet, such as the horseshoe magnet, in such a way that its branches AB and CD are perpendicular to the direction of magnetic field. The two ends of the loop are connected to the two halves X and Y of the split ring. The two halves of the ring have resistive coating on their inner surfaces and are tightly fitted on the axle. The two halves of the split ring X and Y have their outer conducting surfaces in contact with the two stationary carbon brushes E and F respectively. When the circuit is completed as shown in the figure, the current flows in the branch AB of the loop from A to B through the carbon brushes E and F. Since the direction of the magnetic field is from North Pole to South Pole, according to the Flemings left-hand rule, a force is exerted on the branch AB and pushes it down. The current in the CD branch is in an opposite direction to that in the AB branch, and therefore a force is exerted on the branch CD in upward direction. Thus the loop and the axle start rotating in an anti-clockwise direction. After half rotation, the two halves of the split ring X and Y come in contact with the carbon brushes F and E respectively, and the current in a loop starts flowing in the direction DCBA. Therefore, a force is exerted on the branch DC in downward direction and on the branch BA in the upward direction, and the loop continues to rotate in the anti-clockwise direction. Thus, the current in the loop is reversed after each half rotation, and the loop and the axle continue to rotate in the anti-clockwise direction. Commercial motors run on the same principle, but practical changes are made in their construction. You will learn that later. Electromagnetic induction. We have seen in the previous section that if we keep an electric conductor in a magnetic field such that direction of the current flowing through the conductor is perpendicular to the magnetic field, then a force is exerted on the conductor. Because of this, the conductor moves. But if an electric conductor is moving in a magnetic field, or the magnetic field around the stationary conductor is changing, what will happen? In order to find out an answer to this question, research was done by the great scientist Michael Faraday in the year 1831. Faraday showed that an electric current can be produced in a conductor with the help of a moving magnet. Galvanometer. Galvanometer is a sensitive device which works on the same principle as that of an electric motor that we have studied earlier. We can make some electrical measurements with it. A coil is positioned between the pole pieces of a magnet in such a way that the pointer on the galvanometer dial is connected to it. When a small current, for example 1 mA, flows through the coil will rotate. The rotation will be proportional to the current. Voltmeter and ammeter also work on the same principle. In galvanometer, the pointer deflects on both the sides of the zero mark depending on the direction of the current. Collect the material as shown in figure. Complete the circuit by connecting the galvanometer. Keep the bar magnet erect in such a way that its north or south pole is just below the copper wire. Now, if the wire is kept moving from A goes to B, the pointer of the galvanometer gets deflected. This is called Faraday's electromagnetic induction. Now move the magnet with the wire fixed. The galvanometer pointer still gets deflected. Try this. Complete the circuit as shown in figure. Discuss about and select the components as required. This experiment. If we open the plug key and make the current 0 in the coil, the pointer of the galvanometer deflects to a side and quickly comes back to 0. If the current in the coil is started again, the pointer again deflects to the other side and then returns quickly to 0. Now when the electrical current is flowing through the solenoid coil and the solenoid coil is displaced with respect to the coil, the current is still produced in the soil. What can be inferred from these two experiments? Even if the solenoid coil is kept stationary, a change in current in the solenoid coil produces a current in the coil. If the solenoid coil is moved towards or away from the coil, we see a deflection in the galvanometer. Also, the faster is the displacement of the solenoid, larger if the deflection of the galvanometer pointer. A current is produced in the coil, or if the solenoid coil is moved towards the coil, then also a current is produced in the coil. Faraday's law of induction. If a current is switched on or off in the solenoid coil, a current is induced in the coil, such as induction is also observed when the current in the solenoid coil is increased or decreased. Current is induced in the coil when it moves aside from the front of the solenoid. From these experiments, it is understood that whenever the number of magnetic lines of force passing through the coil changes, current is induced in the coil. This is known as Faraday's law of induction. The current produced in the coil is called the induced current. Fleming's right-hand rule. When will the induced current in the electrical conductor coil be maximum? It will be maximum when the direction of motion of the electric conductor is perpendicular to the magnetic field. In order to show the direction of the induced current, Fleming's right-hand rule is very useful. Stretch the thumb, the index finger and the middle finger in such a way that they will be perpendicular to each other. In this position, the thumb indicates the direction of motion of the conductor, the index finger the direction of the magnetic field, and the middle finger shows the direction of the induced current. This rule is known as Fleming's right-hand rule. Introduction to scientist. Michael Faraday, 1791 to 1867, was an experimental scientist. He was not formally educated. Teenager Michael started working in a bookbinding shop. While reading books there, he got interested in science. Sir Humphrey Davy appointed him as a laboratory assistant in the Royal Institute, London. There he discovered the laws of electromagnetic induction and the laws of electrolysis. Several universities offered him honorary degree, but Faraday refused to accept such honors. Alternating current AC and direct current DC. So far we have learned about a non-oscillatory current flowing in one direction in a circuit, from cell to the cell. Such a current is called a direct current DC, as against a current changing in magnitude and direction after equal intervals of time, which is called alternating current AC. The direct current can increase, can be stable, or can reduce also, but it is not oscillatory. This is shown graphically in the figure. Alternating current is oscillatory, as shown in the graph. It increases to a maximum, then reduces to 0 and increases to maximum in the other direction and again reduces to 0. In the figure, magnitudes like -1, -2 have been used to show the reverse direction. The oscillation of the alternating current occurs in a sinusoidal manner with time and hence is shown by the symbol. Direct current flows in one direction, but the alternating current flows in periodic manner, in one cycle, in forward and reverse direction. In India, in the power station generating electricity, one cycle changes in 1/50 second. That is, the frequency of AC is 50 Hz, 50 cycles per second. When the electric power is transmitted over a long distance, it is beneficial to have it in AC form, as it results into minimum power loss during transmission. The home supply is of alternating current AC. We have learned in the previous class about the precaution to be taken while using the electricity. Electric generator. We have seen the experiments based on electromagnetic induction. The current produced in this experiment was of very small magnitude. But the same principle can be harnessed for the use of mankind to produce large current. Here, mechanical energy is used to rotate the current carrying coil in a magnetic field. Figure shows a copper wire coil ABCD kept between the two pole pieces of magnet. The two ends of the coil are connected to the conducting rings R1 and R2 via carbon brushes. Both the rings are fixed to the axle. But there is a resistive coating in between the ring and the axle. The axle is rotated with the help of a machine from outside. Because of this, the coil ABCD starts rotating. The stationary carbon brushes B1 and B2 are connected to a galvanometer, which shows the direction of current in the circuit. Upon rotating the axle, the branch AB goes up and the branch CD goes down. That is, the coil ABCD rotates the clockwise. According to Fleming's right-hand rule, electric current is produced in the branches AB and CD in the direction A goes to B and C goes to D. Thus, the current flows in the direction A goes to B, B goes to C, C goes to D, as shown by arrows in the figure. In the external circuit, the current flows from B2 to B1 through the galvanometer. If instead of one loop coil, a coil consisting of several turns is used, the current of magnitude several times flows. After half rotation, the branch AB takes the place of branch CD and the branch CD takes the position of the branch AB. Therefore, the induced current goes as D goes to C, C goes to B, B goes to A. But the branch BA is always in contact with the brush B1 and branch DC in the contact with B2. Hence, in the external circuit, current flows from B1 to B2, that is opposite to the previous half rotation. This repeats after every half rotation. An alternating current is produced. This is what is called an AC generator. What will be required to make a DC generator? The DC does not change the direction in the external circuit. To achieve this, a split ring is fixed on the axle like a split ring used in electric motor. Because of this arrangement, the branch of the coil going upwards is always in contact with one brush and the branch going downwards is always in contact with the other brush. Hence, the current flows in one direction in the external circuit. This is why the generator is called as a DC generator.